Ever wondered how nuclear physicists simulate fuel assemblies? Today we delve into the second part of our journey into criticality calculations using the Scale Code System 2.3.1. We're taking a deep dive into the world of nuclear physics where the stakes are high and precision is paramount. Imagine being in a bustling control room at a nuclear research facility. The task at hand? Simulating a hexagonal VVIR 440 fuel assembly with a non-uniform axial burnup profile. Sounds daunting, right? But that's just another day in the life of a nuclear physicist. The key to understanding reactor behavior lies in accurately modeling burnup profiles. So we're going to use sorcerer, a sequence within the scale system, to deterministically compute a fission distribution and use it as the starting source in our Monte Carlo eigenvalue criticality calculation. Now, to paint a picture of what this looks like, think of an intricate geometric model with input parameters that require meticulous attention to detail. We're specifying parameters for the VR assembly, including the composition of UO2 fuel, cladding, and moderator, as well as the geometric layout. This includes detailed control settings and boundary conditions to ensure we get accurate results. But we're not stopping there. We're also leveraging DEVC, the denovo eigenvalue calculation sequence, to generate a reasonably accurate starting source. This is a game changer because it enhances our Kino CSS Monte Carlo calculation by reducing skipped generations and improving reliability, especially for loosely coupled fissionable areas. And the significance of this approach? Well, by incorporating a precise starting source from denovo, we're ensuring that our Kino calculation converges efficiently and provides reliable eigenvalue estimates. So, as we fine-tune our parameters and prepare to run some test cases, remember, our ultimate goal is to obtain accurate results efficiently. It's a complex process, but one that holds the key to unlocking new insights into nuclear reactor behavior. So, buckle up as we unravel the complexities of nuclear reactor simulations. Accurate modeling of burnup profiles is not just a fancy term. It's crucial for understanding reactor behavior. When we dive into the world of nuclear reactor simulations, the minutiae of our models can make or break the reliability of our results. These details are not just about the geometric layout or the composition of the fuel assembly. They're about capturing the very essence of nuclear fission itself. That's where the sorcerer sequence within the scale code system comes into play. It's like a master painter, but instead of a canvas, it paints the fission distribution of our reactor core. Sorcerer deterministically computes this distribution, which then serves as the starting source for our Monte Carlo eigenvalue criticality calculation. Now imagine we're simulating a hexagonal VVIR 440 fuel assembly with a non-uniform axial burnup profile. It's a complex task, right? But with the sorcerer sequence, we've got a solid foundation. We specify parameters for the VVR assembly, including the composition of UO2 fuel, cladding, and moderator. We also define the geometric layout, control settings, and boundary conditions. All these details contribute to the accuracy of our results. But it doesn't stop there. We also employ the DEVC, or the denovo eigenvalue calculation sequence. It's like a trusty sidekick to sorcerer, helping to generate a reasonably accurate starting source. This enhances our Kino CSS Monte Carlo calculation by reducing skipped generations and improving reliability. It's particularly useful for loosely coupled fissionable areas. When we compare the fission source distributions from denovo and Kino, we can see the significance of our approach. It's like comparing a rough sketch to a finely detailed drawing. By incorporating a precise starting source from denovo, our Kino calculation converges more efficiently and provides reliable eigenvalue estimates. So you see, accurate modeling isn't just about the details. It's about the big picture. It's about taking these complex calculations and distilling them into something precise, reliable, and understandable. This is where the magic begins, creating an accurate starting source for our calculations. Now take a deep dive into the intricacies of the input file. Our focus in this segment is the input file, a key element in our Scale Code System 2.3.1 simulation. This file holds the blueprint for our VVIR 440 fuel assembly model, detailing the composition of the uranium dioxide fuel, the cladding, and the moderator. The geometric layout of the assembly is also catalogued here, capturing the hexagonal structure of the Vivier design. But it's not just about the nuclear materials or the geometry. The devil, as they say, is in the details. Look closely, and you'll find a set of control settings and boundary conditions. These aren't just arbitrary numbers or placeholders, they're critical in ensuring that our simulation behaves as close to reality as possible. Now we've set the stage, but where does the performance begin? That's where Sorcerer comes in. It's a sequence within the scale system that we're using to deterministically compute a fission distribution. This calculated distribution serves as the starting source for our Monte Carlo eigenvalue criticality calculation. But we're not stopping there. We're enhancing our process even further by leveraging the denovo eigenvalue calculation sequence, or DVC. With DVC, we generate a reasonably accurate starting source, which not only reduces skipped generations, but also improves reliability, particularly within loosely coupled fissionable areas. This process, intricate as it may be, is crucial to our goal of achieving accurate criticality calculations. It's like fine-tuning an instrument. Each control setting, each parameter, each boundary condition must be precisely calibrated. That's how we ensure the melody of our simulation rings true. As we move forward, remember that our goal is not just to run a simulation, but to create an accurate and efficient representation of a nuclear reactor. And each step, each decision, brings us one step closer to that goal. With careful parameter selection, we're one step closer to accurate results. Let's bring in the big guns now, the de novo eigenvalue calculation sequence. In this complex world of nuclear reactor simulations, the DEVC sequence is our secret weapon. It's like having a supercharged engine under the hood of our calculations. The DEVC sequence is a powerful tool that we employ to generate a reasonably accurate starting source. This starting source is the springboard for our criticality calculations. It's like setting the stage for a play. The better the stage is set, the more smoothly the performance runs. But why is it so important to have an accurate starting source? Well, imagine trying to solve a complex puzzle without having the correct pieces to start with. It would be pretty tough, wouldn't it? That's why we use the DEVC sequence. It helps us get the right pieces in place right from the start. Now, this doesn't just make our calculations faster, it also makes them more reliable, particularly when dealing with loosely coupled fissionable areas. You see, these are areas where the neutrons are not strongly interacting with each other. In such cases, having a good starting source is critical to avoid skipped generations and to ensure that our calculations converge efficiently. With the DEVC sequence, we're able to enhance our Kino CSAS Monte Carlo calculation. This is a powerful combination that allows us to tackle complex reactor simulations head-on. It's like having a high-powered microscope that lets us zoom in on the smallest details and understand the behavior of our reactor. But we're not just running these calculations blindly. We're constantly fine-tuning our parameters and running test cases to validate our approach. This iterative process allows us to continuously improve our models and ensure that our results are not just accurate, but also reliable. So, in essence, the DEVC sequence is one of our most important tools. It's like the compass guiding us through the intricate maze of nuclear reactor simulations. This step ensures that our calculations are not just efficient, but also reliable. So, what's the big deal about using an accurate starting source, you might ask? Well, when it comes to criticality calculations, it's all about precision and efficiency. By incorporating a precise starting source from de novo into the Kino calculation, we're ensuring a more efficient convergence and reliable eigenvalue estimates. It's like giving our calculation a head start. You see, the fission source distributions from de novo and Kino can be likened to two runners in a race. While both are capable, de novo, with its accurate starting source, takes the lead, reducing skipped generations and improving reliability, especially for loosely coupled fissionable areas. This results in a more streamlined and efficient calculation, saving valuable time and resources. So, whether you're a seasoned nuclear physicist or just an enthusiast, keep in mind that in the world of nuclear physics, every detail matters. And there you have it, a deep dive into the intricacies of enhanced criticality calculations. Remember, in nuclear physics, accuracy and efficiency are key.